Hello everyone, I am Dr. Navin Agrawal, Professor and Head Department of ENT, Index Medical College Hospital and Research Center. Today I am discussing with you the physiology of hearing and balance. So, physiology of hearing. We hear by funneling sound from the environment into the outer ear and causing the tympanic membrane to vibrate. Those sound waves vibrations are transferred into mechanical vibrations to the ossicles. Those mechanical vibrations cause the oval window to move back and forth, causing the perilymph of the inner ear to begin wave-like motion. The perilymph fluid motion is transferred to the endolymph, that is potassium rich, and the wave motion is transferred into electrical impulses picked up by the hair cells of organ of corti and sent to the brain via the cochlear nerve. The round window is responsible for absorbing the fluid wave vibrations and releasing any increased pressure in the inner ear caused by the wave. This is the flow diagram of the hearing mechanism in the outer ear or from the ear to the cochlea and the nervous system. As you can clearly see, airborne sound which is collected by the auricle, then external canal, which is transferred over the tympanic membrane. The vibrations over the tympanic membrane will be carried out towards the stapes footplate, and from the footplate of the stapes, it causes the vibrations. It sets the vibrations in the inner ear, perilymph, and ultimately leads to the vibration or displacement of the basilar membrane, and basilar membrane shearing movement of the basilar membrane and the tectoral membrane causes the electrical impulses to generate out of the mechanical energy, and which is carried out by the auditory pathway up till the auditory cortex, and ultimately we hear the mechanism of hearing. Mechanical conduction of sound. Mechanical conduction of sound is three parts via the pinna, axon canal, and the middle ear transformer action. Then transduction of the mechanical energy to electrical impulses at the level of cochlea, and then conduction of electrical impulses to the brain via the from the cochlea via the auditory pathway to the mid auditory cortex. Mechanical conduction of sound. Pinna receives sounds from 135-degree arc of respective side and helps localization and concentrate sound and increase sound pressure. That is 6 decibel. Axonometry canal along with pinna increases sound pressure by 15 to 22 decibel for 4000 Hz frequency. Impedance matching function of middle ear to convert sounds of greater amplitude and less force to greater force and lesser amplitude. So, what is the middle ear transformer? It consists of many ratios. The first is catenary lever, that is 2 times gain of sound pressure at malleus. Ossicular lever 1.3 is to 1 times gain. Then hydraulic lever. Hydraulic lever, that is the aerial ratio 55 mm square of the tympanic membrane as that of the 3.2 millimeter square of the stapes footplate. That is around 14 is. So 14 into 1.3 is equal to 18 is to 1. That is the overall transformer ratio of the middle ear. Phase difference also plays a role, that is reciprocal action of OW and RW. That means oval window and round window. This is the structure of the cochlea. You can see perilymph in the scala vestibula and scala tympana, and endolymph in the scala media, where the tectorial membrane and the basilar membrane lies, that is the organ of corti, where the transaction takes. The transaction means the conversion of mechanical energy into electrical impulse. Mechanical energy coming outside of the environment via the sound wave is coming towards EAC, and it is striking over the tympanic membrane, which is causing vibrations of the ossicles, and ultimately the vibrations leads into the perilimb, which causes the vibration of this endolymph and the tectorial membrane movement, which ultimately transducts the mechanical energy into electrical, and that is why how we hear the sound. Next slide. Organ of corti. So, what is the organ of corti? These hair cells are transition. As the basilar membrane bellies in and out, it pushes and pulls the complex of tissues above. The hair cells of the organ of corti ride with the basilar membrane. The hairs have their tops embedded in the tectorial membrane and their roots fixed in the hair cell. So, the motion of the basilar membrane bends and twists and pulls and pushes the hair. Under this physical stress, the hair generate electrical signals which stimulate the auditory nerve, also known as the acoustic nerve and the eighth cranial, a bundle of about 30,000 individuals. Eventually, in a way still not fully understood, the electrical signals running through the auditory nerve stimulate the hearing centers of the brain. In the cells of the auditory cortex lies the mystery of the sensation of hearing. Transduction of cochlea. With sound stimulus, basilar membrane and organ of corti move up and down, causing sideways bending of sterocilic, sterocilia, opening channels to allow potassium to flow into hair cells, resulting depolarization. Depolarization spreads to lower part of cells, causing calcium channel to open, which causes transmitter vesicles to fuse with basal part of the cell membrane and release transmitter substance, that is amino acid, glutamate, which diffuses across synaptic cleft to initiate action potential in auditory. This is the diagram for electrical responses of hair cells. Endolymph in scala media has a positive potential of plus 80 millivolt and high potassium dependent on adequate and is produced by stria vascular. When potassium is driven into cell by this big potential gradient, large voltage is given, causing a natural impulse. Generated by outer hair cells at apical region, it produces the AC current waveform of stimulating sound and represents potassium flow through outer hair cells. CM absent when outer hair cells damage is a the DC potential that follows the envelope of stimulating sound arising from inner hair cells, rectified derivative of sound signal. Auditory nerve action potential is a discharge in nerve produced at the presence of stimulus. Functions of organ of Cartwright. It converts mechanical energy into electrical energy. It dispatches to the brain a coded version of the original sound information, not only about fundamental frequency, but about intensity and timbres as well. Send electromechanical signals into the central nervous system. Functions of hair cells. There are two types of hair cells. One is outer hair cells and one is the inner hair cells. Outer hair cells, they shorten and lengthen on exposure to sound due to the protein pristine. Amplify sound after input from inner hair cells. Sharpen the frequency. Inhibitory effect by decreasing responsiveness. Cochlear microphonics. Otoacoustic emissions. Inner cells, they are the classic auditory receptor cells and send signals to the brain about specific sound. Differences between the inner and outer hair cells. You can see in this table There are certain features which are described, such as cell number. So, inner hair cells having the 500 cells number, while outer hair cells have the 12,000 cell number. Rows, it is in one row and it is in 3 to 4. Shape of the inner hair cells is like flask, and while the outer hair cells are like cylinder. Afferent fibers mainly supplies the inner hair cells, and efferent fibers mainly supply the outer hair. The inner hair cells develops early, while outer hair cells develop late. The main function of inner hair cell is to transmit auditory stimulus, while the main function of auditory outer hair cell is to modulate inner hair cell function. More, inner hair cells are more resistant for ototoxicity, while it is less sensitive, outer hair. More resistance for high intensity noise, the inner hair cells, while the outer hair cells are less sensitive for the high intensity. OAE generation is possible in outer hair cells, while it is not possible in the inner hair cells. Theories of hearing. There are different theories for hearing. First is Helmholtz theory, that is placed in 1883. High frequency basal region, low frequency apical region. Tuned resonator like a Rutherford's theory. It is proposed in 1886. That is also known as the telephone. Weaver's-Woolley resonance theory, that is proposed in 1949, combines about two theories, that is Helmholtz theory and Rutherford's. Von Becke's traveling wave theory in 1960, wave begins from base and moves to up. Region of maximum displacement varies according to frequency. Those are the different theories for hearing, out of which nothing can be established properly as a single theory. This is the hearing pathway. You can see in this diagram, this is medial olivary nucleus, and this is the lateral and medial trapezoid cord. And from here, lateral lemniscus from midbrain, and midbrain to thalamus, and thalamus to cortex. You can see this diagram by yourself. I'm pausing here for some time. Okay. So, transmission from cochlea to brain. The cochlea to brain transmission system contains 30,000 nerve fibers coming from the organ of corti to form the auditory nerve. Fibers are grouped by the frequency of the sound signal. Coming from the brain, descending nerve fibers may carry instructions from the brain back to the ear, filter out and thus eliminate some signals which the brain itself are of no importance and concentrate on others. After passing through the cochlear nucleus, some of the descending nerves from the brain go to middle ear where they control the muscles used for fending off dangerously loud sound. The nerve fibers carrying sound signals lead to different parts of the auditory cortex depending on the frequencies they carry. The auditory cortex lies in a deep furrow called the high tones terminate deep within the sylvian fossa, while the low tones end near the surface. This is the conduction of electrical impulses to the brain, hair cells, that is peripheral or spiral ganglion, cochlear nerve or auditory nerve, then ventral and dorsal cochlear nucleus, then superior olivary nucleus, via which they goes into the lateral lemniscus, then inferior colliculus, medial geniculate body, and ultimately they reach the auditory. You can also remember it by the that is AC mechanism of Bell. Mac 1875 identified role of vestibular system. Circular canals and autonomous organs is stimulated by a mechanical rotation of head and linear and gravitational acceleration, respectively. Sensitivity to tilt of 5 degree. Transduces transducer mechanical energy to electrical impulses interrupted by the brain to allow conscious awareness of position and movement. Vacuole neutrical static labyrinth, semicircular canal for dynamic labyrinth, VOR and VSR. Vestibulo ocular stimulation of the sensory cells. Stimulus to vestibular sensory cell is shearing motion of cupula or statoconical membrane. Movement of sterocilium towards kinocilium produces depolarization with increase in frequency of nerve impulse and vice versa. Here you can see the movements and displacement of sensory neuron, the sensory here for the depolarization, which gives us the or gives the brain sense of position. Mechanism of action, cupula and macula. This is the diagram showing the mechanism of action. Crista of lateral semicircular canal cells are polarized towards utricle, that is utricopetal. Crista of superior and posterior semicircular canals are polarized away from utricle, that is utrico. Utricle hair cells polarized towards stereocilia and secure away from the stereocilia. Evolves law. Head and eye movement always occur in the plane of canal being stimulated in direction of endoluminal flow. Ampulopetal flow causes greater response in horizontal semicircular canals. Ampulopegal flow causes greater response in vertical canals. This is the Ward's law. Vestibulo-ocular reflex. Head rotation to right causes utricupital movement of right limb endolimb and depolarization of crista. Simultaneously, there is utricupital movement of endolimb in left ear causing hyperpolarization. This results in contraction of left ear rectus, left lateral rectus, and right medial rectus, and the eye deviates to left. That is the slow phase of the nystagmus. The stimulus is very strong to contain the compensatory movement within the limits of orbit. A fast movement in the opposite direction occurs, that is fast phase, mediated by the reticular formation, directing ocular muscles nuclei to return eyeball to the point of gaze from where slow phase begins. Thank you.